Hello. You guys are familiar by now with polynomial functions, but we're going to dive into polynomial functions even further by looking at the graphs of them. And as we dive into this, it's always good to do a quick recap of some of the skills that you've already covered. We're looking at functions basically of the form f of x equals a times x to the n for these polynomial functions. And you've already explored the basic ones. Like, let's say you have f of x equals x. You already know that the graph looks basically like this. You know that when f of x equals x cubed, you know that the graph looks basically like this. I'm just doing quick sketches. F of x equals x to the fifth. It's basically the same idea, just a little more exaggerated there in the middle. Or if you have some of those even exponents, like f of x equals x squared, you know, you have your nice little parabola. If you have f of x equals x to the fourth, it looks kind of like parabola, but it flattens out here on the bottom. And then f of x equals x to the sixth, same idea, but flattens out even more. So, you know the rough idea and the rough shape. And there's, some other features that we've talked about. Like for these odd degrees, we've talked about domain. So in this case, for the odd degrees, domain negative infinity to infinity, range negative infinity to infinity. They're increasing on the entire domain. So like if you trace from left to right, they keep climbing up and to the right. So if you're looking to the left, if you're tracing to the left, it looks like they're falling, and if you're tracing to the right, it looks like they're rising. Whereas the even ones down here, you have your domain of negative infinity to infinity, but your range is gonna, in these particular ones, is restricted 0 to infinity. You can have shifting and stuff, so that 0 might not be the actual number, but we're just looking at these basic graphs where a is 1 right now. They are continuous. All these graphs are continuous on their domain, whereas these are decreasing from negative infinity to 0. So like if you're tracing from left to right, they're falling down, and then increasing from 0 to infinity. So as you get to 0, start tracing from there, and then they're going up. So they look like they're rising. If you like trace to the left, they look like they're rising. If you trace to the right, they look like they're rising. So that's just kind of the rough thing that you talked about in the previous lessons about these. Looked at continuity. So if you can trace them without picking up your pencil, then they're continuous. All of these are continuous across their entire domains. So you looked at those kinds of things. Another thing you looked at, especially in college algebra, was some of the features. So looking again at f of x equals a times x to the n, you know that when that a is bigger than 1, you have a vertical stretch. You know that when it's between 0 and 1, you have the, sorry about that. My finger grazes it, and this program, it just immediately erases everything. So let me start over there. So we have the vertical stretch. Oops. Sorry. 0 less than absolute value of a less than 1. That's a vertical shrink. Okay, how I like to think of that is like, just picture if you took the graph and grabbed the top and grabbed the bottom. Vertical stretch, you'd pull it apart. Vertical shrink, you'd squash it together. So vertical stretch, it'll look taller and skinnier. Vertical shrink, it'll look shorter and fatter. Or wider. If you have a negative a, that reflects across the x-axis. If you take your function and add something to the end of it, that shifts up k units. If you subtract something, that shifts down k units. If you take it and add or subtract from the x, so like x minus h to the n, that translates right h units. If you have x plus h in there in those parentheses, that translates left h units. To me, like up and down is what I would think. Plus goes up, minus goes down. But with right and left, it's opposite of what you would think to me. Plus goes right. I'm sorry, plus I would think goes right, but it actually does the opposite and goes left, and then minus goes right. And then you can combine them. So like if you have f of x equals a times x minus h to the n plus k, then you've got a whole combination of those translations. Okay, so let's take a look at a couple of these just to play with what's going on. Like f of x equals x cubed plus 1. Well, let's go ahead and graph f of x equals x cubed, and then talk about what's happening when you do the plus 1. So like on that grid, if I go ahead and put x cubed on there, you'd have 0, 0, 1, 1, negative 1, negative 1, and then it shoots up, like at 2, it shoots up to 8, negative 2 shoots down to negative 8, etc. So it basically looks like this. But as soon as you do that plus 1, that takes the same graph and shifts it up 1. So the 0, 0 goes up to here, the 1, 1 goes up 1, negative 1 goes up 1. So it's the same idea for the graph, it's just shifted up 1. This one's continuous from left to right, and this is increasing from negative infinity to infinity. If you have something like f of x equals x minus 2 to the 5th, with the x minus 2 in parentheses, I mean, you could take your f of x equals x to the 5th graph and look at it. Okay, the x to the 5th graph, you get 0, 0, 1, 1, negative 1, negative 1. At 2, it shoots way up. So this one's shoots up really fast. I'm not going to sit here and draw the whole grid. But then when you do the x minus 2 to the 5th, that minus 2 in parentheses tells us that we're shifting to the right by 2 units. So everything moves over here to the right by 2 units. So same idea with the shape. The shape didn't change, it's just it's moved over to the right. It's also increasing on negative infinity to infinity. Trace it from left to right, and it's making its way up, up, up. All right, let's look at maybe one more. F of x equals -1/2 x plus 3 to the 4th plus 5. All right, a lot going on there. All right, your original graph, f of x equals x to the 4th, is roughly this. Well, let's see here. Original graph, f of x equals x to the 4th. You have 0, 0. You'd have 1, 1. You'd also have -1, 1. Because when you raise a negative number to an even exponent, it comes out positive. And then 2 to the 4th. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Do I have enough space to get 16 on this? Don't think so. Maybe I do. Nope. You know 16's way up there. So you basically know that this graph's going to be kind of flat down here. And this is going to shoot way up. That's that kind of parabola looking shape. A little flatter on the bottom than your usual parabolas you're used to. But what's happening with the function that we're given? Well, that x plus 3 tells us that it's going to have to shift left 3. That -1/2 tells us it reflects across the x-axis and vertically, since 1/2, just looking at the 1/2, since 1/2 is between 0 and 1, that's where you have that vertical or vertical shrink or compression. So it's going to look fatter, like the base is going to be even wider and flatter than it is now. And then that plus 5, well, that shifts it up 5. So for this graph, if you wanted to do a little XY table, you can be like, well, since I know it's going to go left 3 and up 5, you know, if I plugged in -3 for that left 3, I have a good idea of where I expect this to go. I expect the y to be 5. That takes care of the shift left 3 up 5 for that 0, 0 point. Might be a little hard to imagine what's happening otherwise. You know that there's been a reflection across the x-axis. So you know this thing's going to be upside down. But you also know there's that vertical shrink by 1/2. So, you know, when you plug in -2 and -4, you might have an idea about how that's going to look. If I plug in -2, I get 4.5. If I plug in -4, I also get 4.5. So before I had those points 1, 1 and -1, 1. Well, now that distance there's is reduced by 1/2. If I plug in -1 and 2, 4, -5, what does that do? Well, negative 1 can be 2. 2 times 2 is 4. 8, 16. Half is 8. Negative 8 plus 5, that's negative 3. So negative 1, negative 3 would be a point. And negative 5 should give me negative 3 also. But I always like to do it and double check to make sure I didn't make a mistake earlier. Negative 16, so 8 plus 5. Oh my gosh, my head. All right. Negative 8 plus 5 is negative 3. Okay, so negative 5, 1, 2, 3, 4, 5, negative 3. There we go. So now we have that one. I apologize for this. I'm trying to, it's very awkward trying to draw this because I can't rest my hand on the iPad while I'm trying to sketch. It just messes it up. But there you go. So there's that function. All right, so you're like, okay, that's good review. But surely they don't all look like this. And if you were thinking that, you are correct. Because things don't always fit these exact patterns. Like as you're familiar now, when you're working with these polynomial functions, sometimes you start factoring them and they can look pretty wild when they're factored. And all kinds of things can be happening. So our goal today is to look at some general patterns and how to take this further and be able to graph any polynomial function. Okay, so what are some of the things that we need to think about when we're taking this further? Okay, for one thing, we might think about what's happening with our zeros and our domain and range. A couple of things that just suggested from these different graphs. If you have polynomial function f of odd degree, then there's at least one real value of x. That satisfies f of x equals 0. All right, so what is this saying? Well, those odd degrees, they tend to have shapes like this or like this. So what this is saying is if you're dealing with an odd degree, at some point it's going to have to go through the x-axis. It might go through the x-axis more than once, but at least at some point it has to go through the x-axis. So you're going to have at least one value, one real 0. But you could have more. You could have, you could have quite a few more. If you have like x cubed, you could have 3 of them. If you have x to the 5th, you could have 5. It depends on what's happening. So that's just something to keep in mind. Now, if you have even degree, f of even degree, you can think about the pattern that was happening there too. It's going to have a range of the form negative infinity to k or k to infinity. Notice the brackets on k. For some real number k. Because if you're dealing with your even degree, I mean, we looked at some that look like this. They can also be squiggly. They can be squiggly. They can be upside down. They can be squiggly upside down. But either way, on the left, they're either going up. Like on the left and right, the behavior is the same. Like if it's going up on the left, it's going up on the right. If it's going down on the left, it's going down on the right. So you're looking at like some k value somewhere. So you could have from k to infinity, or you could have k and negative infinity, depending on what's happening there for your range. So those are some things to think about with the pattern. Now to take this further, those zeros and their multiplicities tell us actually more than that. The zeros and their multiplicities help us see behavior. At the zeros. Okay. Let's say C is your 0. If there is a multiplicity of 1, then the graph either goes straight through, going up, or straight through going down, just depending on how your graph looks. So it'll just cross the x-axis at C. If it has an even multiplicity, then you will see it do a bounce or turn at C. So kind of like this, see, or kind of like this. So just rough sketch to give you an idea of what's happening. If you have odd multiplicity greater than 1, then you're going to see the graph cross and be tangent at C. So they say it wiggles. If you hear them say wiggles, that's what they mean. So like it can be going like this, or you could have it going like this. Right there at C. So those are some examples of in behavior. Or I mean, zero behavior, sorry. Thinking ahead, not in behavior. Just what's happening at those zeros as it crosses. I'm getting to in behavior very soon. Okay, comment on turning points. Polynomial function of degree n. Has at most n minus 1 turning points. With at least 1 turning point between each successive pair of zeros. Think about it, if there's 2 zeros, then the graph's going to have to turn around and come back to, after crossing once, it's going to have to come back and cross again. So this is another little comment. Like let's say you have a x cubed type function. I'll say cubic because we're not going to limit it to ax cubed. It could be a little more complicated than that. But let's say you have something like that. And let's say it goes like this. So this is degree 3. And you have zeros, 3 real zeros in this example. Right there. Well, successive pair of zeros would be here and here. And notice that there's a turning point. You know, it goes through the x-axis and it has to turn around and come back to get through the x-axis again. And then between here and here, there's a turning point. So that's just something to think about too. Like when you're graphing this, you're going to have those turning points in order to get it to come back. Now to end behavior. I know I was eager earlier to talk about end behavior. Kept slipping and saying it. Okay, interesting thing with the end behavior too. So I guess the best way to, I mean, your book goes through and does this formal definition. All right, let's say, okay, let's have an odd degree first. I don't like always starting out with formal definitions. And we're talking about ax to the n being that dominating term of your function. So you can have other terms, but that's going to be the dominating term, the first one. If you're talking about odd degree, you can look at your a. If it's greater than 0 or less than 0, that's going to tell you a lot. Greater than 0. As x goes to infinity, then f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. All right, what the heck does that mean? Basically, you're looking at your end behavior, it's going to be like this. So if you're dealing with an odd degree like cubic, 3, 5, 7, 9, something like that, and you want to know about the end behavior, well, going to the right, it's going to shoot up. If you're heading to the left, it's going to shoot down. If a is less than 0, it's switched. It's going to go like this. As you're going to the left, it's going to shoot up. As you're going to the right, it's going to shoot down. So as x goes to infinity, as you go to the right, the graph is going to shoot down to negative infinity. And then as you go to the left, x goes to negative infinity, the graph is going to shoot up to positive infinity. That's for odd degree. Even degree, that's the one that looks kind of like parabolas. Might have some squigglies in there. Again, the A basically tells you like cup up, cup down kind of thing. As absolute value of x goes to infinity, f of x goes to infinity. As absolute value of x goes to infinity, f of x goes to negative infinity. So what is that saying? Well, for the positive a, your end behavior to the left's going to go up, to the right's going to go up. If a is less than 0, to the left it's going to go down, to the right it's going to go down. That's basically what that's saying. Just like the parabolas, you know, if when a is positive, it holds water. When a is negative, it dumps out water. Same idea here. That's basically what that's saying too. So like if you had a function like f of x equals negative x to the 4th, I forgot the negative sign, sorry, plus 2x squared plus x minus 8, that leading term, they call it dominant in this book, but usually they say leading term in other books. Negative x to the 4th, we're going to focus on that. Well, a is negative 1, which is less than 0, and this is even. So then we know that the end behavior should be like this. If we have something like f of x equals negative x to the 5th plus x to the 4th minus 3x squared plus 2, again, we're just focusing on that negative x to the 5th, that leading term. Once again, a is negative 1, which is less than 0, but this is odd. So then we know for this one that the end behavior would look you know, something like that. All right, what do you say we dive into graphing and do as much, like do about, I think I have 2 examples that I want to try to do here in this video. This is just part 1 because this video is going to be super long. But let's do some graphing and let's put all of these things together. Talking about the zeros, how to find them, talking about multiplicity, talking about what's happening at the zeros, what's happening at the end with the end behavior, all that good stuff. Plotting our intercepts, connecting the dots. Let's do it. All right, let's start with the function f of x equals 2x cubed plus 3x squared minus 11x minus 6. Like, we want to graph this, so we need a lot of information in order to do so. Now, remember a little while ago, not too long, we had to go through that process of trying to find zeros and trying to figure out the factorizations and all that stuff. You're gonna, like, thinking back to your possible rational zeros. Your p's and q's. Like your p's plus minus 1, plus minus 2, plus minus 3, plus minus 6. Your q plus minus 1, plus minus 2, and then p over q. You end up with plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus a half, plus minus 3 halves. I think I got them all earlier. Let me quickly in my head just trying to double check. Yeah, I don't see any more right now. All right, and if you've applied Descartes' rule of signs, I'm not going to do that right now on this, but you can go do it for yourself. Then you will quickly see for the positive that there's one positive zero involved. So you can just you can just ignore, like, for now, you can just start trying positive numbers. I honestly tried 1 first and it didn't work. But when I tried 2, that worked. So let's do a synthetic division by 2 so that we can break this down. Yeah, that remainder of 0 tells me that 2 works. So I have a factor of x minus 2, and then now I know I have a factor of 2x squared plus 7x plus 3, because the 2, 7, and 3 there in the quotient. And then I can take 2x squared plus 7x plus 3 and apply some of my other skills and factor that, 2x plus 1, x plus 3. So it's the same f of x, it's just now it's factored. If you multiply all that out, it'll give you back that f of x. All right, so our zeros are 2, negative 1/2, negative 3. So that's all important information. Now what else is important? So that's my zeros are my x-intercepts. My y-intercept, remember you do that by plugging in 0. So if you plug in 0, if I plug it into those factors, I'll have negative 2 times 1 times 3. So that gives me negative 3 halves. Something didn't work out there, sorry. Negative 2. That's negative 6. What am I saying negative 3 halves for? Oh my gosh. Okay. It's getting late. Okay. What else do we know? We know that these zeros have multiplicity 1. Each one has multiplicity 1. Like when you factor, it's in factored form, they don't have any exponents on each factor. It's just x minus 2 raised to the first power, 2x plus 1 raised to the first power, x plus 3 raised to the first power. So that tells us that the graph's going to cross the x-axis at each 0. So that gives us an idea of things to look at. And then when we look at that leading term of 2x cubed, a is positive, this is an odd degree, so then we know the end behavior is going to look like this. What's in the middle was to be determined, but that's going to be the end behavior. All right, let's get started. Let's start graphing this lovely thing. I don't think I need much more than that on the x-axis, but I definitely need more on the y-axis. Sorry about my y-axis. It's so hard for me to draw that without like turning my hand. Not so great at doing the vertical axis with trying to control my hand here and not touch the iPad screen. That'd be awful if suddenly this all disappeared. I have to start over. I gotta find a different way to do this. Okay, anyways. So for now I'm stuck. We can plot some of the points we know. Like we know at 0, -6, it's going to cross the y-axis because that's the y-intercept. So we can plot that. We can plot the zeros. That's where it crosses the x-axis. So at 2, -1/2, and -3. Since we know the end behavior, we know it's going to actually cross at those zeros, like go right on through, and then we know the end behavior, so we have an idea about some of the other values that we might want to look into. So I like doing a little XY table just to get a few more values to plot. And that would give me a better idea of the shape. So 1, 2, 3. So if you plug in, I especially like to see what's happening like between the zeros. That tells me a lot. All right, now we're not going to cover just yet how to find exactly where the peaks and valleys go, but we can get rough ideas by plugging in some values. So we can plug in like a -2, because that's between those zeros of -3 and -1/2. So we can plug that in, and we get, let's see here, if we plug in -2 into the factors, we have -4 times -3 times 1. So that gives us 12. So at -2, 12. That's why I had to do 12 on here on the y-axis. Let's see here. So I think that's right there. I'm also blind in one eye, so sometimes it's hard for me to, my depth perception's a little off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Yeah, I'm good. All right. So then that gives me a rough idea about where this thing is peaking. I went ahead earlier before starting this and I put this in Desmos. And Desmos tells me that the peak is actually at -1.943, 12.028, but that's all right. We don't need to know that much detail. But we have at least a rough idea about where this thing's peaking. So it's going to come down like this, and then it's coming down here. I have a pretty good idea that it's going to, well, I know it's going to have to go through this point because of the way the zeros are, the multiplicity. But let's see, I think I plugged in 1. And when I did that, like if I plug it into the factors, -1 times 3 times 4, that's -12. All right, so that gives me, did I go down 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There I am. So -1, -12 right there. don't think it's perfect on the graph. Yeah, 0.943 comma negative 12.028 would actually be that value. But you know what? We're not learning how to find that exact value yet. So close enough. So at least we've got the basic rough shape of this graph. And I'm sure on your graph paper, you're going to be able to do a much better job than me at that. But there you go. That put together all these things that we're learning. Since you know the in behavior, you can double check it. Like you knew the in behavior, so you knew that once it crossed, it gave us 3 zeros for a cubic function. So that's all of our zeros. So you know that on that far left zero, that in behavior, it's going to have to go through and then go down to infinity. And then on the far right on that zero, it's going to have to go through and go up to infinity. And then it has 3 zeros on 3 real zeros, so it's going to have 2 turning points. And that's that high and that low. I mean, technically, that's not the highest point, because remember this graph, it's going to keep going down forever. It's going to keep going up forever. But in the future, you're going to talk about relative minimum, relative maximum. And that's where those peaks and valleys, those turning points come in. When you get into calculus, you'll start doing derivatives to help you start looking at where those are. That's so much fun. All right. One more. I know this is long-winded, but I really want to do another example. And we're not even done with this lesson yet. But this is the last example I'm going to do for this video. F of x equals x plus 2 cubed. They were generous and went ahead and gave it to us in factored form. And then times x minus 1 squared. So what are we going to do there? Well, we can see immediately where the zeros are. We can see there's one at negative 2 with multiplicity of 3. We can see that there's one at 1 with multiplicity of 2. So since the one at negative 2 has a multiplicity of 3, that is an odd multiplicity that's greater than 1. So it's going to be crossing and tangent to the x-axis there at that one. Cross and tangent. And then since 1 has a multiplicity of 2, which is an even multiplicity, it's going to turn or bounce there at 1. So at least we know kind of what it's going to look like when it's doing that. Our leading term, well, we don't need to multiply the whole thing out, but if we multiplied it enough, we would know that the leading term is an x to the 5th. Just need to know that, basically. So the a is 1, which is positive, and we're dealing with an odd situation here. We're dealing with an odd degree. So with that, we can look at what's happening with our end behavior. Remember that tells us a lot about our end behavior. We say n is odd. So if that's happening, then the end behavior is going to look like this. Now, this graph particularly has a lot going on in between there, but that's just telling us the end behavior, what that looks like. Finding out what f at 0 is important because that's the y-intercept. So you have, what, 8 times 1, which would be 8. So 0, 8 will be our y-intercept. And what else do we want to know? Probably need some more values in between, but let me start just sketching what we know. We're definitely going to need some more values. Okay, by the time I finish teaching this course, maybe I'll get pretty good at drawing this. While I'm drawing, I'll chat. It kind of like my ice skating. Like if you hadn't read my little biography, I like to ice skate, and this summer I took lessons on how to play ice hockey, but I am nowhere near. I'm not going to be in the women's team league yet. I'm hoping to join a C League team soon. But anyways, C League's like beer league, but that'll be fun. But anyways, with the skating lessons, like it can be slow progress, but then all of a sudden things click and it gets better. So like learning to draw the straight lines on this iPad without messing it up feels like trying to master a skating technique. Yeah, okay. So those zeros are at -2 and at 1. So we can plot those. Y-intercept's at 8, 2, 4, 6, 8. So we can plot that. And yeah, we know the end behavior, but you know, I'm gonna enjoy like finding some values just to make sure I understand like exactly how steep things are. And just a little quick recap on those zeros. Remember, with the zeros, the -2, 0 and the 1, 0. These are zeros. These are also x-intercepts. So you're like, yeah, we just did that. Yeah, I know. And also x plus 2 and x minus 1 are factors. So all of that comes together here. It's kind of nice to see it, like all those facts. All right, anyways. Now I think we don't have our calculus knowledge to do derivatives and figure out where exactly the relative minimums and maximums are. But we can at least pick some x's, plug them in, get some better ideas, and then connect the dots. That's all we can do right now. So I picked -3. I picked -1. I picked... What else did I pick? I think I picked 1/2. I mean, if you want to pick more, like -1/2 and stuff, you can. And I picked 2. So I was just trying to get a better handle on how fast things were shooting up or down or whatever. If you plug -3 into that factored version, you have what? -1 cubed, which is -1, times -4 squared, which is 16. So you get -16. Okay. Did I go 16? No, 16's off the grid. But at least you know that this is going to be really drastically like dropping down here. So it gives you a good idea about what's happening there. When I plugged in -1, 1 cubed is 1, and -2 squared is 4. So I got 4. So -1, 4, 1, 2, 3, 4. Just kind of gave me an idea about what's happening there. Oh, but remember, with our behavior, at -2 it crossed and was tangent. I should have paid attention to that. So technically, it should have this little, almost like a hurricane eye shape, but like in the hurricane symbols, it's be tangent and cross right there. And then at 1, it's gonna turn or bounce. But this thing actually, if I did it again on the Desmos, and the very tippy top's at -0.2, 8.398. So that's not actually the very tippy top, but you know, that's all right. Without Desmos, you're not going to know that. So this thing's going to come back, crashing back down. And I think I plugged in a 1/2 to see what would happen next. And when I did, I put that in the calculator and I got around a 3.9. Hopefully I did that correctly. So 1, 2, 3, so pretty close to right there. So at least that gave me an idea about like how drastically that was coming down. But then at 1, it's supposed to turn or bounce. So you want it to come like this. And then I plugged in the 2. 4 cubed is 64. And then 1 squared is 1. So that's 64. And then like, oh, that's super sharply going to shoot up. I'm not going to hope to actually plot that point, but at least I have a good idea about the shape. Looking at my Desmos graph, of course, it's not much nicer because it's going to be more accurate, but it's basically got a shape like this. So I mean, that's probably a better idea, but there you go. So we used all that information that we just learned plus what we previously were learning. Zeros was easy this time because of the factored form, but looking at multiplicity told us a little bit more about being careful with sketching that graph. So like that -2 had to cross and be tangent, so it was like this right here, and then that 1 had to turn or bounce, so it was like this right here. And then we knew about the end behavior. You know, to the left it's shooting down, to the right it's shooting up. And then I picked a couple of extra values to plug in to really get an idea about like how drastically things were moving. And that was it. All right, so I think that's where I'm going to pause or stop for this lesson. We're going to come back and talk about the intermediate value theorem and the boundedness theorem and do a couple more examples, but I feel like this is a good place to kind of take a break because there's a lot. The next video will probably be a lot shorter, but still, I didn't want to overwhelm you. But thank you for joining me, and I will see you again soon.